Hi everyone, I'm Redha Gouicem and I'm going to talk to you about dynamic frequency scaling on modern processors and its interaction with the scheduler. I'm going to present a new problem we discovered, frequency inversion, and how we leverage dynamic frequency scaling in the scheduler to improve application performance. This is a joint work with Damien Carver, Julien Sopena, Gilles Muller and Julien Lawall from Sorbonne University and Inria, Baptiste Lepers and Willy Zwaenepoel from the University of Sydney, Jean-Pierre Lozi from Oracle Labs and Nicolas Palix from the University of Grenoble. One of the key characteristics of a processor is its frequency. It is directly related to performance as well as energy consumption. For more than 20 years, it has been possible to dynamically change the operating frequency of processors. This enables to save energy by lowering the frequency when the CPU is not in use. In setups where performance is key, frequency is increased when applications are running at the expense of energy consumption, while embedded setups might choose to keep the frequency low to save energy at the expense of performance. Let's make a quick recap of how dynamic frequency scaling works. On most multi-core CPU, frequency is managed at the chip level. All cores on the same chip share the same frequency. Here, if CPU 0 has a load of 30% and all other cores are idle, the frequency of the whole chip is raised. If CPU 0 starts to run applications that require more performance, the frequency of all CPUs is raised to a higher level. Idle CPUs consume more energy because of busy CPUs, not because they need it to. When all CPUs are fully loaded, CPU vendors guarantee that they will all run at least at the nominal frequency, which is usually the one written on the box when you purchase the processor. Additionally, most modern CPUs provide a turbo mode. When some CPUs are idle, the maximal operating frequency of the other CPUs can exceed the nominal frequency. Here, CPU 0 is the only one busy, so it is able to run at a higher frequency than previously. All other CPUs are idle, but must still maintain the nominal frequency. Turbo frequencies are the only frequencies managed individually for each CPU. However, this is not true on new processors anymore. The latest generations provide per-core frequency scaling. Intel implements this feature in its 2019 Cascade Lake architecture with the speed select technology. AMD also provides this feature on its latest Ryzen CPUs. Each core can now individually manage its frequency. Here, if CPU 0 is the only one executing software, it will be able to use the maximal turbo frequency just like before. However, all other CPUs that are idle will now be able to run at the lowest possible frequency. These idle CPUs will therefore use less energy than previously. Even when most cores are running, per-core frequency scaling is beneficial. Each core is now able to use a frequency that matches its current load. This offers the ability to make a compromise between performance and energy savings. Previous work mainly focuses on changing the frequency of the processor in order to match the needs of the workload. To this end, Linux provides scaling governors. These governors are algorithms that choose the operating frequency of the CPU with regards to different metrics. The latest one, schedutil, uses data from the scheduler to determine the current load of the CPU and chooses the frequency accordingly. Recent Intel CPUs also provide such a governor implemented in hardware. It uses metrics such as the number of retired instructions to determine the current load and infers a frequency. Academic works propose to use dynamic frequency scaling for different goals, such as maximizing the number of instructions executed per joule consumed, reducing contention on shared resources like caches by slowing down CPUs, or reducing energy usage, mainly for embedded systems. Up until recently, not much has been done in terms of frequency awareness in the scheduler. In the last couple of years, the Linux community introduced TurboSched to place small jitter tasks on cores using turbo frequencies, or even more advanced support for heterogeneous architectures like ARM's Big Little. However, while studying the behavior of the Linux scheduler, we discovered a new problem related to dynamic frequency scaling that was never mentioned. We exhibit this new problem through a case study, the compilation of the Linux kernel. Our hardware setup consists of a 4-socket machine. Each chip is a 20-core Intel Xeon E7-8870 V4 processor. With hyperthreading enabled, this makes a total of 160 cores. In terms of frequency, the CPU features per-core frequency scaling, even though it is older than the Cascade Lake architecture mentioned earlier. The nominal frequency is 2.1 GHz with up to 3 GHz with turbo mode enabled. This table shows the relation between the number of active cores on a chip and the maximal turbo frequency. For example, with 4 active cores, the maximal frequency is 2.7 GHz. With more than 8 active cores, turbo frequencies cannot be used. The machine runs on a Debian Buster with a Linux 5.4 kernel installed. this kernel is the latest long-term support version released in November 2019. For clarity purposes, the following slides will only present the compilation of the scheduler subsystem of Linux instead of the compilation of the whole kernel. We trace the frequency of each core during the compilation, with each line representing a different core. We log the frequency at runtime with hardware registers at each tick. We noticed two surprising things on this trace. First, during these two phases, only a few cores are running, but they are running at a very low frequency. We would expect to see some cores using turbo frequencies higher than 2.1 GHz with a low number of active cores. And even if they are not using turbo frequencies, we should at least be able to use the nominal frequency, 2.1 GHz. Second, in these more parallel phases, most cores are used and the system seems highly loaded. Again, even if turbo frequencies are not available due to the number of active cores, we would at least expect to be running at the nominal frequency. In these phases, as with both red phases, most cores are running at the lowest possible frequency of 1.2 GHz and not at the nominal frequency of 2.1 GHz. This means that during these phases, we are provided only half of the frequency that we would expect. In order to find out why this is happening, we zoom in and study in more detail a smaller time window of this trace. This trace is the same as the previous one, but zoomed in a 100 millisecond window at the beginning of the compilation. In addition to the frequency, the thickness of the line indicates if the core is busy or idle. Busy cores have at least one thread running on them, and idle cores have nothing to run. We see an interesting behavior on this trace. In the region circled in red, busy cores run at frequencies between 1.2 and 1.7 GHz, which is lower than the nominal frequency. These cores are busy for a few milliseconds and become idle while the frequency is still low. Shortly after becoming idle, the frequency of these cores starts to rise and attains high values. We can even see cores running at turbo frequencies while being idle. On this workload, the latency of the frequency scaling makes these changes useless. The frequency is raised when it no longer needs to be raised. The load of a core and its frequency are mismatched. Let's try to understand how long it takes for a CPU to change its frequency. The frequency transition latency, or FTL, is the duration between a change of load on a core and the change of the frequency to match this load. We measure this latency on our machine by running a busy loop pinned on an idle core. The rest of the machine is idle. We measure the time between the start of the loop and the moment the frequency reaches its maximum value, as well as the time between the end of the loop and the moment the frequency goes back to its lowest value. With this metric, we measure the time needed to take the decision, which is the job of the scaling governor, and the actual time it takes for the frequency to change in hardware. On our machine, with the default scaling governor, power save, it takes 29 milliseconds for the frequency to rise from lowest to highest frequency. Conversely, it takes 98 milliseconds for the core to go back to a low frequency after the end of the workload in order to save energy. Changing the frequency of a CPU is not instantaneous. This means that a task starting on an idle core must wait 29 milliseconds before being able to fully utilize the CPU. And if the task completes in less than 29 milliseconds, it will have never run at full speed. And indeed, on the previously shown traces, lots of tasks complete their work in less than 30 milliseconds. In terms of scheduling, this also means that two CPUs with different frequencies are not equivalent in terms of computing capacity, even when sharing a chip. And this state can persist for tens of milliseconds. Let's now see how the Linux scheduler, CFS, operates when placing newly created or waking up threads. With this knowledge, we will be able to understand why our kernel build runs on low-frequency cores when it should not. When a thread is created or waking up from blocked state due to an I/O, for example, the broad idea of CFS is to look for the least loaded CPU to place it on. When idle CPUs are available, they are obviously viewed as the least loaded CPUs. Indeed, CFS tries to be work conserving, which means that if idle CPUs are available, no work should be waiting to run on an already busy CPU. In our case study, we observe a recurring pattern, the fork system call, closely followed by the wait system call. Since CFS strives to achieve work conservation, it keeps waking up idle CPUs while busy CPUs become idle. The beginning of the compilation of Linux is actually quite sequential. There are never more than a couple of threads that actually run concurrently. By constantly using idle CPUs for newly created threads, CFS uses many CPUs while only a few were actually necessary. Combining the long-frequency transition latencies and the placement algorithm of CFS that prioritize idle CPUs creates the actual problem, frequency inversion. We define frequency inversion as a state where the frequencies at which two cores operate are inverted as compared to their load. In other words, the least loaded core runs at a higher frequency than the most loaded one. With this problem defined, we propose two solutions to solve it that we implement in Linux. But first, let's set up a scenario to explain our solutions. We first show the behavior of CFS in this scenario. If a thread calls the fork system call to create a child thread on C0, the placement algorithm of CFS chooses C1, an idle core, as the destination core for this newly created thread. The child thread is immediately placed on C1 and starts running while the parent thread resumes its execution. Both cores are used, everything is okay. Now, if the parent thread immediately calls the wait system call after the fork, C0 becomes idle. A busy core becomes idle while an idle core becomes busy. This situation is prone to cause a frequency inversion. Now, let's see the first solution we propose, local thread placement. We call this strategy slocal. The idea is to have the most simple and naive solution to our problem. In the previous situation, we would have wanted the child thread to keep using the same core as its parent. So, let's try to force a local placement strategy in CFS. As previously, a thread runs on C0, calls the fork system call, and CFS chooses C1 as the destination core for the child thread. Instead of this decision, we force the placement of the child thread on the same core as its parent. For threads waking up, we place the waking up thread on the same core as the waker. We now have a core with two threads, C0, and the core that remains idle, C1. In the good scenario, the parent thread quickly blocks and the child thread is scheduled. A single core is used for this sequential work, problem solved. However, if we backtrack a little bit in our scenario, we can see a serious problem. What if the parent thread does not block and keeps running? In this case, core C0 will stay overloaded until something forces one of the two threads to move to another core like C1. In CFS, this something would be load balancing. The load balancer is triggered periodically and will try to even out the load between cores. Here, C1 is idle and C0 is overloaded. C1 will therefore steal one thread from C0. Both cores are now used and the situation is solved. The problem, however, is the duration of this period of imbalance between C0 and C1. This situation can go unchanged for tens of milliseconds in CFS. In this case, this means that the child thread could stay on C0 for tens of milliseconds before being migrated to C1 and being able to run. This strategy solves frequency inversion, but heavily relies on the balancing mechanisms of CFS to work. Let's see how this translates with our case study. Here is the frequency trace of the compilation of the scheduler subsystem of Linux with the default CFS scheduler, as previously shown. Now, here is the execution with our slocal strategy enabled. During the phases that use the tens of cores running at the very low frequencies, with CFS, we now only use less than 5 cores running at very high turbo frequencies. For example, the first green phase took 1.5 seconds to complete with CFS and less than a second with slocal. The more parallel phases, with more threads running at a low frequency instead of the nominal one with CFS, are now using less cores and higher frequencies in the turbo range. Performance-wise, the compilation is 24% faster than with CFS, and energy-wise, we also save 24% of the energy used by the CPU as compared with CFS. The energy savings are directly due to the reduced execution time. For this workload, waiting for periodic balancing to even out the load is not a problem. Once threads are spread out, they keep creating their children on the same CPU, maximizing the frequency used. Now, let's see our second solution, deferring thread migrations. We call this strategy smove. The main idea is to take advantage of local placement if there is a potential gain of frequency, and to avoid relying too much on the periodic load balancer of CFS like slocal. We start with the same situation. A parent thread creates a child thread with the fork system call on C0, and CFS chooses an idle destination core, C1. Before placing the child thread on C1, we first check this core's frequency. If C1 is running at a high frequency, we behave in the same fashion as CFS and place the thread on C1. If C1 is running at a very low frequency, instead of immediately placing the child thread on C1, we place it on C0. Additionally, we arm a timer that will be triggered in 50 microseconds. C0 now has 2 threads and the parent thread keeps running. 50 microseconds later, the timer interrupt is triggered. If the child thread has not been able to run yet, the interrupt handler will migrate the child thread to C1. This is the worst case scenario where we'll lose 50 microseconds of execution time. However, in the best case, here is what happens. During the 50 microsecond window, the parent thread stops using the CPU because of a wait system call, for example. The child thread is then scheduled on C0. When this happens, we cancel the timer. In this situation, we avoid using two cores for a sequential program. We use a core with a high frequency and avoid waking up an idle core. Let's see how this translates with our case study. Again, here is the default trace with the default Linux scheduler. And here is the frequency trace with the S-move strategy. The resulting trace is quite similar to the one with our local placement strategy. The quasi-sequential phases still use less cores at a higher frequency. And the parallel phases now run at least at the nominal frequency, leaving some cores idle. Performance-wise, the compilation is 23% faster than with CFS, and we save 21% of energy. On our case study, S-local and S-move behave similarly. Overall, we use less cores than CFS, and these cores run at higher frequencies. However, both strategies differ in their design. S-local is quite aggressive, as it completely removes the placement algorithm of CFS by always placing threads locally. It is a simple, naive solution that only necessitates 3 lines of code. However, since it heavily relies on periodic load balancing in order to avoid oversubscription of some cores while other cores are idle for a long period of time, it probably has some workloads where it will have poor performance. S-move, on the other hand, is more balanced in that it only changes the behavior of CFS if gains are possible frequency-wise, and tries to avoid oversubscription for long periods of time. It is, however, more complicated with 124 lines of code and the introduction of a potential large number of timers. In addition to our case study, we evaluate the performance and energy usage of both of our strategies. We do this on 60 applications from 2 benchmark suites, NAS and USENIX, as well as on Hackbench and Sysbench OLTP, 2 well-established benchmarks in the Linux scheduler community. NAS is a set of high-performance computing applications, and USENIX features a large spectrum of workloads, ranging from web servers and databases to deep neural network libraries and CPU-heavy applications like compilation and compression. We evaluate both performance metrics and energy usage on 2 machines: the 80-core Intel server used in the case study and the smaller 4-core AMD desktop machine. We also evaluate 2 scaling governors, PowerSave and ScheduTil. We want to show that our work is orthogonal to scaling governors in the sense that governors change the frequency to match the load, while we change the scheduling decisions to leverage the frequency of the CPUs. Here is the performance and energy improvements of S-local in red and S-move in blue as compared to CFS on the Intel machine with the PowerSave governor. Whatever the metric, higher is always better. We do not display all 60 applications because it would be unreadable. We only show the subset of applications with more than 5% difference in terms of performance with CFS. Overall, we see more applications that benefit from our strategies in terms of performance than applications that are deteriorated. S-local and S-move have respectively 27 and 23 applications that outperform CFS. We also see up to 58 and 56% improvement for applications that heavily feature the fork-way pattern like Perl benchmark. On the other side of this bar plot, on the left, we see that only 4 and 3 applications are deteriorated by more than 5% with S-local and S-move respectively. Here, we see the first large difference of performance between S-local and S-move. The aggressive strategy of S-local causes catastrophic worst-case scenarios as expected. The NKL DNN benchmark's performance is deteriorated by 80% as compared to CFS. S-move, on the other hand, is a low-risk strategy with worst degradations of 8.4% on the Hackbench macro benchmark. The 32 remaining applications have similar performance with or without our strategies. In terms of energy, both strategies perform better than CFS on most applications. Most of the gains are due to the improved performance, like in our case study. However, we also observe that some applications have higher energy savings than performance gains. For example, this Sysbench OLTP benchmark has the same performance with CFS and S-local, but saves energy with our strategy. This can be explained by the fact that less cores are used, hence the save energy. From these results, we think that S-move is the better solution since it provides very good performance gains and limits the losses. We invite you to take a look at the paper for the full results on both machines. We also provide an evaluation of the power save and schedule governors, and we show that S-move has a negligible overhead. We detail the worst-case scenarios of our strategies and explain why they occur. To summarize our work, we present the frequency inversion problem that stems from long-frequency transition latencies, frequency-agnostic schedulers, and per-core dynamic frequency scaling. We propose two solutions, S-local and S-move, that we implement in Linux and thoroughly evaluate. Both strategies are publicly available on our GitLab at this address. We also identify and discuss future work. First, a fully frequency-aware scheduler that would use a frequency heuristic in the same fashion as existing locality heuristics. Second, creating a model of the behavior of the frequency of a CPU in a given setup, since frequency can be influenced by factors like the number of active cores, temperature, or the instruction set used. This model will be very useful to design a fully frequency-aware scheduler. Finally, shorter FTLs with faster frequency reconfiguration would also mitigate the frequency inversion problem. This should be addressed at the scaling governor level. Thank you for your attention. Feel free to take a look at the paper and contact us for more information.